Awesome, great. Any questions at all before we get started? Things going all right? Okay, well, let's see if we can finish up this section today and get into some new stuff, which is based on this stuff anyway. So we say it's new stuff, but it's not really new. Let's do this last problem on the ones we were doing last time. Basically, we were using the sum and difference formulas to rewrite these expressions that were involving inverse trig functions, and then using the same kind of techniques that we did earlier in the semester to rewrite the composition of trig function with inverse trig function using triangles and getting it as an algebraic expression. Right? That's what we were doing at the end of class last time. So notice here, again, we've got an inverse cosine and an inverse sine here. I've got different, actually it wouldn't even matter if I had different arguments or not inside those functions. I can think of those as angles, right? Because again, when we're doing inverse functions, we think about putting in a number and getting out an angle. When we're doing inverse trig functions. So if we call this alpha and we call this beta, how would you rewrite tangent of alpha minus beta? Not worrying about what alpha and beta area are to start with. Just if I had tangent of alpha minus beta, how would we rewrite that to start?
Tangent alpha minus tangent beta over 1 plus tangent alpha tangent
Good.
beta.
So remember, it's for your tangent sum and difference formulas. It's a sum or difference on the top. It's a product on the bottom. The sign in the middle on top matches the one for that's in the middle on the left-hand side. The sign on the bottom is the opposite sign. So since we have tangent of alpha minus beta, it's a minus sign on top, a plus sign on bottom. That's literally just the formula for the difference formula for tangent, right? Okay. So the way we got this, at least in this particular case, is we said we were going to let alpha be that first piece and that beta be the second piece. So let's see if we can, again, use our knowledge of some right triangle stuff to help us rewrite these compositions as algebraic expressions. And again, what I mean by algebraic expression, we're getting rid of the trig function. An algebraic expression is something that only involves addition, subtraction, multiplication, division, and roots. Combinations of those things. So exponents are allowed because exponents are just repeated multiplication, right? So when we have trig functions, those are not algebraic expressions. We refer to trig functions, exponential functions, logarithmic functions, is what we call transcendental functions, that we can't express them in an algebraic form. I don't really care that you know that word, but just make sure when I say, what I really want you to understand is when I'm saying something is an algebraic expression, I mean it looks like something you did from algebra class from high school. Okay. It doesn't have trig functions in it. That's what I mean by an algebraic expression. Okay. All right. So remember when we did the triangles last time, the first thing we did was rewrite each of those equations, right? So how can you rewrite the first equation without an inverse trig function in it? How can you rewrite that equation with alpha as another form without the inverse part in it? Good. Cosine alpha equals x, and then the other one will be sine of beta equals y, right? And then again, we created right triangles to help, because notice that in what we're trying to simplify, over here, we want tangent of alpha and tangent of beta. So if I can use the right triangle here, I should be able to read those off the triangle. We did before. So we have cosine of alpha is equal to x. So what sides can we label?
Adjacent and hypotenuse.
Okay, and the adjacent will be
X.
and the hypotenuse will be 1. And then we can figure out the opposite side with Pythagorean theorem, right? Opposite side will be what?
Square root 1 squared minus x squared.
Good. Yep. So we'll get square root of 1 minus x squared for that one. For the triangle with the beta in it, what sides can we label? Yep, the hypotenuse and the opposite. The opposite will be, and the hypotenuse will be the 1. And then notice that your adjacent will look a lot like the other one, right? Square root of 1 squared, square root of 1 squared minus y squared again, your Pythagorean theorem. Everybody see that? That's okay? All right, so now let's look at the expression that we're trying to simplify again. We want tangent of alpha and tangent of beta. Looking at the triangles, what is tangent of alpha?
Square root of 1 minus x squared over x.
Good. Our tangent of alpha, we can use opposite over adjacent, right? Opposite side is square root of 1 minus x squared. Adjacent side is x. So it's just the ratio. How about your tangent of beta? Good. And then it'll be the same expressions on bottom. You know, I said that Dr. Olson could throw something at me if I'm too loud. I start throwing something over at her. She starts being too loud, right? Is that problem okay? Do you think I care to simplify that? Ooh. Just leave it like that. It's okay? Again, we talked about that trig substitution in the last section, and then we had those problems on the quiz, and we went over those problems that were on the quiz last time as well. And then we have this being able to rewrite these as algebraic expressions like we were just talking about. That pops up later. Those two concepts together of being able to do a trig substitution and then being able to go back to an algebraic expression pops up later in math. In particular, it pops up in Calc 2. So it's one of the reasons why we go through it. I mean, besides the obvious reason that it's all sorts of fun, we do use this stuff later. Any questions on any of those three? The two that we talked about at the end of class last time, or this one? Are those okay? We happy? Great. Okay. So let's see if we can finish off this section talking about sinusoids. Yeah. So what do we mean by a sinusoid? So one of the things that you do in modeling is that if you have repetitive data, maybe temperature data over the course of a year, or maybe you have sales data over the course of a year, which also fluctuates up and down depending on the season, or maybe you're looking at tides, which go up and down. Anything that fluctuates that you're trying to model looks like a wave, right? Or if you're doing frequencies of radio waves or magnetic waves or whatever, doesn't matter. Anything that has waves to it kind of looks like a sine or a cosine function when you grab it. Graph it? Graph. Anyway, it looks like a sine function. So that's what we mean by a sine function, a sinusoid. Its graph looks like a sine function. So we defined that a little bit more precisely with what the form of the function has to be. So a sinusoid is a function of the form f of x equals a sine of, I'll call it bx plus c. This is what we're going to try to do to create these sinusoidal expressions. Okay? So this is what we mean by a sinusoid. It's something that has some amplitude piece out front, and it looks like a period change and a phase shift in the sine function. Notice we don't have an up or down piece for defining what a sinusoid is. It's literally just this. It's a function that can be written as sine of something and then a constant multiple of it. That's what we mean by a sinusoid. All right, so our goal here is going to be able to rewrite these expressions, where I notice I have a typo because when I typed this up, I hit an H apparently. I mean as a sinusoidal expression, not has. Okay. Spell check doesn't catch things like that. Of course, the program I use doesn't have spell check unless I explicitly run it, so can't really use that as an excuse anyway. But I want to rewrite this as a sinusoidal expression. So what I mean is that I want to try to combine this together to make it look like this form. I want it as sine of a sum of things. Okay? That makes sense? That's what I'm trying to get to. All right. So to do this, that requires us to go back and remember what our pardon me, what our sum and difference formulas look like for sine. So remember that, I'll just write down the sum formula. Remember that your sine formula is sine of alpha cosine beta plus sine beta cosine alpha. Right? Okay. Pardon me. Notice that this has a sine of theta in the first term. So I could think of maybe that being my sine of alpha, replacing the alpha with a theta. It has a cosine theta in the second term. So I can put that over here too. All right? So notice that I've got kind of half the form. I've got a sine of theta in the first term. I've got a cosine theta in the second term. I kind of got half of the sum formula here, right? The trick to this is I need to figure out a beta so that I can see the cosine of beta here and the sine of beta here. Okay? That makes sense so far? Right. So I've got to do a little bit of work so that I can actually see an angle where I can put those pieces in there. So let's look at this A and this B here. And we're going to play with those values. In particular, here's what I'm going to do. I'm going to put my beta in my right triangle. I'm going to make my adjacent side A and my opposite side B. Now, why did I choose to form it this way? I just said I want to replace cosine of, I want to see cosine of something, right? Is in that first term. If I want to see cosine of something, remember in a right triangle, cosine is adjacent over hypotenuse, right? So that's why I put the A on the adjacent side. For that same beta, I want to see sine of beta, which is what, and I want that in that second term, so that's why I put the B on the opposite side. Okay, that's why I created the right triangle this way. Okay. Doing that, what would you get for the hypotenuse if I create my right triangle this way? The square root of a squared plus b squared. Good. Use Pythagorean theorem, I would get square root of a squared plus b squared. Now, just looking at the right triangle, you should be able to tell me what sine of beta is and what cosine of beta is literally from the right triangle. What is sine of beta from the right triangle? Not worrying about any other expression anywhere else. If we have the right triangle set up this way, what is sine of beta? Good, yeah, it's opposite over hypotenuse again, right? It's b over square root of a squared plus b squared, right? Cosine will be what? Good, yep. So it's adjacent over square root of a squared plus b squared. That's nothing new, right? We've done that stuff before. Now, the reason why I created the triangle this way, because again, I want to see cosine of beta on the first term, and I want to see sine of beta on the second term, right? That's why I created it this way. But notice, in order to using this right triangle, in order to see sine beta and cosine beta, I don't just have an a and a b. I've got a over square root of a squared plus b squared and b over square root of a squared plus b squared, right? Which I'm missing currently, correct? But I can get it in there. I can be fancy. That's what we do in math. We get fancy. Actually, in math, we just usually cleverly rewrite things. It's a lot of stuff we do. We cleverly rewrite things, right? We cleverly rewrite 0 or we cleverly rewrite 1. For example, when you add fractions, you cleverly rewrite 1, right? If you get common denominators, okay? We're going to do that exact idea here. We're going to cleverly rewrite 1 to introduce what we need, okay? So I'm going to start with my a sine of theta plus b cosine theta, and I'm going to multiply it by 1. I'm going to cleverly rewrite 1 as square root of a squared plus b squared over square root of a squared plus b squared. I didn't change anything, did I? As long as a and b aren't both 0, I didn't change anything. If a and b are 0, I just did a really bad thing and divided by 0. Which means I probably just, introduced the apocalypse or something. Okay. All right, so now I want to see a over square root of a squared plus b squared and b over square root of a squared plus b squared. So I'm going to take the denominator, essentially, and distribute it to both terms and leave the numerator out front. Okay? So we'll write this as square root of a squared plus b squared times a over square root of a squared plus b squared sine of theta, and then b over square root of a squared plus b squared cosine of theta. See what I did there? Just took the denominator and distributed it? Or think about it a little bit more for maybe precisely. I rewrote this as the top times 1 over the bottom and then distributed that fraction through. So again, now that we have the way we have things set up, this piece here is your cosine of beta. This piece here is your sine of beta. Right? So you would get this is going to be square root of a squared plus b squared sine of theta plus beta. The only thing that you have to figure out is what is beta. Beta is going to be a number. You're going to have a number for a and a number for b. So beta is really going to be a number. Beta is going to be an angle where we have the cosine of beta is equal to this expression and the sine of beta is equal to this expression. So that's what we get to the end. Okay. So when you have these things with a sinusoidal expression, the first thing you're going to do is multiply and divide by the square root of the sum of the squares of your coefficients, and then you're going to figure out what your beta value is. Okay, we'll do a couple of examples like that here in a minute. But just to summarize at the bottom here of the page, this is going to be equal to square root of a squared plus b squared sine of theta plus beta, where beta is the angle, oops, for heaven's sake, with cosine of beta being a over square root of a squared plus b squared, and sine of beta equaling b over square root of a squared plus b squared. I shouldn't say the angle. I should say the angle between 0 and 2 pi. I mean, we have one period around, if you will, to figure out what the beta is. So you'll have to figure out what quadrant you're looking at when you do this. But we've talked about those before, right? Like if you had both sine and cosine are positive, you're in quadrant 1. If sine's positive and cosine's negative, you're in quadrant 2, and so on. So you can figure out what the beta value is. It's okay? All right. So let's see if we can do some examples. That sounds like fun. All right. So let's do the first one here. It asks us to rewrite negative 3 sine x minus 3 root 3 cosine x in terms of just sine. By the way, you could also do the same game in terms of just cosine. It's the same kind of process, so you're only going to be asked to do this in terms of sine alone. But you can do the exact same for cosine if you really want to. All right, so again, first thing you want to do, figure out what square root of a squared plus b squared is. That's what you're going to multiply and divide by. Okay? All right, so square root of a squared plus b squared is going to be square root of 9 plus, because negative 3 squared is 9, negative 3 root 3 squared will give you 27. So you get 6. First thing you want to do is that. Okay? And that's what we're going to multiply and divide by. All right? So we'll have our negative 3 sine x minus 3 root 3 cosine x is equal to 6 times negative 1/2 sine x minus root 3 over 2 cosine x. So again, remember, we're going to multiply by that square root of a squared plus b squared out in front, and then we're going to divide each of the coefficients by that square root of a squared plus b squared. 3 over 6 is 1/2. 3 root 3 over 6 is root 3 over 2. Okay? That's step 1. Figure out that square root of a squared plus b squared and multiply and divide by it. Okay. Again, this number right here, and again, I'm using beta. I don't really care what letter you're using for the angle. This was our cosine beta, and this is our sine beta, correct? First, personally, I would identify what quadrant we're even looking for the angle in. Make sure we have the right quadrant, okay? Some of these problems, you're going to have to use your calculator to get the angle, okay? You won't figure out, in the first two, we can get the exact values here. But in general, you're going to have to use your calculator. Remember when you do inverse sine or inverse cosine on your calculator, it only gives you half of what you look for, right? Inverse sine gives you an angle in 1 or 4. Inverse cosine gives you an angle in 1 or 2. What happens if your angle's in a different quadrant than what you're doing the inverse for, right? So you have to pay attention to what quadrant you're looking at. This one says that your cosine is negative and your sine is negative. What quadrant are you in if both sine and cosine are negative? Third, right? So my beta that I'm looking for is in quadrant 3. Okay? Just by those things. All right, I'm going to write that down. You don't have to write this down every time, but just to explain why, your cosine of beta is negative and sine of beta is negative, so beta is in quadrant 3. Yes?
Can you say one more time how you got the -1/2 sine x minus root 3 over the cosine x?
So we found this 6.
Okay.
Okay? We multiplied and divided by 6. So the 6 stays out in front.
Okay.
I distributed the 1/6 through.
Oh, okay.
So the 3 over the 6 is a half, and the root 3 over 6 is root 3 over 2. That's where that came from. Yep. Yeah. That's an important step. We got to know where those numbers came from. Yep. But in particular, if I'm looking for an angle that has a sine and cosine for those things, they have to be less than 1. Right? So I need to make sure that I have the right values there. Good question. All right. Now let's ignore the negatives. Do you know an angle, a reference angle? Maybe make it a reference angle. Do you know a reference angle that has a cosine equal to a half and a sine equal to root 3 over 2? Cosine is a half. Sine is root 3 over 2. Which angle does that for your reference angle? Yeah, 60. So put it in radians, it'll be 5 over 3, right? So the reference angle is pi over 3. You're in quadrant 3. What angle do you need? Oops. I'll probably use that little tilde for the reference angle, like we talked about before. Oops. 7 pi over 3 will get you all the way back around in quadrant 1 again. 4 pi over 3, good. So since we're in quadrant 3, we'll use the 4 pi over 3. So then your final answer will be that. So your final answer is your 6 stays out in front. It's sine, because that's how we're rigging it to make it the sum formula for sine. It's whatever's on the inside here for the x, or inside the sine and the cosine, so the x comes first, and then plus the beta that we just found, which is 4 pi over 3. Questions on that one? We're going to do more. Is this one okay so far? I know, a little weird to wrap your head around the first time. I agree. Let's do another one. We've got 7 sine of 3x minus 7 cosine of 3x in terms of just sine. Good news is that 3x, we're not going to do anything with it except making sure that we have the 3 attached to the x at the final answer. So the 3 is not going to do anything different at all. Okay? So don't even, if you want to, ignore the 3, just make sure you write it in your final answer and then you're done. I'll talk about what I mean in a minute. First thing we want to compute is what?
You want to find out these square plus b squared is?
Good. Yep. First thing we'll do, if this is your a and this is your b, we want square root of a squared plus b squared. You'll get 49 plus 49, or 49 times 2, which is 7 root 2. We get square root of 9, so 7 root 2. I figured you could do the arithmetic, so I didn't bother going through all the steps. Okay, that's the first thing. Next thing we want to do with that number is what? What do we do with that 7 root 2 now?
We divide it.
Oh yeah, we'll multiply and divide it, right? So the 7 root 2 that we're multiplying by will hang out in front. And then we'll divide also by 7 root 2. So 7 over 7 root 2 will give you 1 over root 2 sine of 3x minus, and you'll get another 1 over root 2 cosine of 3x. Again, these numbers here are coming from the fact that I'm dividing 7 by the 7 root 2 and the 7 by the 7 root 2. That's where the 1 over root 2's come from. So far, so good? Okay. We need to figure out an angle that gives us 1 over root 2 for its cosine and negative 1 over root 2 for its sine. Right? The number in front of sine of 3x is the cosine of the angle. The number in front of cosine of 3x is the sine of the angle. It's the opposite of what the function that you see on there, right? Because that's not what the sum formula for sine looks like. First, again, like I did before, the cosine is positive, the sine is negative. What angle, what quadrant am I looking at? If cosine is positive and sine is negative, what quadrant? Fourth, right? So again, just to write this down, if this is your cosine of beta and this is your sine of beta, you don't have to write the arrows and point. I'm just doing it so you can keep track of what's going on, right? Your cosine beta is positive and sine of beta is negative. That tells us that beta is in quadrant 4. Now notice that your sine and your cosine have the same, if you ignore the negative sign, the sine of beta and cosine beta have the same value, 1 over root 2. What angle are you talking about for a reference angle if they're both 1 over root 2? Pi over 4, right? Pi over 4 is a reference angle. We're in quadrant 4 though. So what angle do you want to use? Negative pi over 4 works fine. Yep, absolutely. You can also use 7 pi over 4. Either one works. If they're coterminal, that's perfectly fine. So if you'd rather write negative pi over 4, that's fine. And then for their final answer, then we're just about done. So again, the reason why we did all of this work is because we now recognize what's in the parentheses as your sum formula for sine. Just technically it's difference formula for sine the way we have it. But your sum formula for sine is in here, right? That's what we have. So we can use sine of, the first thing we'll write is what's inside the sine and the cosine function. So that's where I said the 3 doesn't really matter. Just make sure you have it at the end. That's what's inside the sine and the cosine. And then whatever the beta value is here, you're just going to add it on the end. So it's sine of 3x minus 4. If you want to check your answer and make sure you've done this correctly, probably the easiest way to check your answer is to take your calculator or go to the computer, go to a graphing device, graph this expression, graph this expression. If the graph's exactly the same, what I mean by that is if you graph that one and then you graph this one and nothing changes, you've got the right answer. You're getting the same graph. That's probably the easiest way to check your answer. Just graph them both and see you get the same graph. I would do that in here, but the Wi-Fi is so terrible in here, I'm not sure it'll actually... No, it says it's on. Let's see if it really is on. I have a computer over here and it tells me that it's not connected to the internet. So If you don't have a graphing calculator, if you're familiar with Desmos, it's a great, I think we've used it here before, but it's great. All right, so the one was 7 sine 3x minus 7 cosine of 3x. And zoom out a little bit. That's what that looks like. The other one we just typed in was 7 square root of 2 times sine of 3x plus, minus pi over 4. And it landed right directly on top of it. And if you're unsure that it actually landed right directly on top of it, you can actually turn these off and on. And notice that you get the same thing. It goes right over the top of it. We really did do it correctly. We did great. I'm glad we spent the time on it and did it right. It would suck if we spent the time on it and didn't do it right. That okay? So far, so good? All right. So notice the first two examples we did. We were able to figure out the exact values, right? Notice in this next example that we have, the exact value is probably going to be a little bit more difficult. Okay. So this is why I said it's important to keep track of which quadrant you're in, so that when you use your calculator to find the angle, you use your calculator to find the angle, you're finding the correct angle. Because again, when you use inverse sine or inverse cosine, you've got the range restricted for those. Okay, first step. Notice, by the way, this is written in the opposite order. Which one's playing the role of A now? Which one's your A now? The -9, right? The A is on the sine, the B is on the cosine, the way we're doing this, right? So what is the first step? What do we figure out first? Good. Square root of A squared plus B squared. Square root of 81 plus 169. Oh, what is that? 250? Did I do that right? 250 has a 25 in it if you want to be fancy. You're going to write as 5 root 10. We're not going to be able to figure out the exact value for the angle in this case. So if you want to leave it as square root of 250, you can, because you're just going to type it in your calculator anyway to figure out what the angle is. Okay. What do we do with that value now? Multiply and divide. Good. So I'm going to go ahead and reorganize so I keep track of which is which. So I don't mess things up, because I like to mess things up. I'm going to put the sine first and the cosine second. So we'll multiply by 5 root 10 and divide each coefficient by 5 root 10. The 5 root 10 goes out in front, and the 5 root 10 also goes in the denominator for each coefficient. So far, so good? All right. So again, remember, the first number here that's attached to the sine is your cosine of beta. The one that's attached to the sine is, attached to the cosine is your sine of beta. Cosine is negative, sine is positive. What quadrant are we looking in? Second, right? So again, we have our cosine of beta is negative 9 over 5 root 10. Sine of beta is 13 over 5 root 10. So
This tells you that beta is in quadrant 2. See if I can find my calculator real quick on here. It's in some random folder that I discovered this morning. Hopefully I can get to this. There it is. I want to show you that we're going to get the same answer either way. That's why I'm trying to get the calculator to load, if it will. Maybe. Oh, it says it's loading. Oh, hey, there it is. All right. So, okay. I gotta need my keyboard. That way. It's a calculator emulator. Literally, I have to turn the calculator on. It's emulating it that much. I have to turn it on. All right. So the first thing you want to make sure you do is make sure you're in radians. Your angle will be in radians. Okay. So make sure you do that first for these. Okay. All right. So going back to what we have written, you can use either function to calculate the beta. You should get the same answer. So I could do the inverse cosine or the inverse sine. I should get the same answer. There will be a be careful moment here in a second. Okay? I just want to show you what happens. So the first one, we would quit. For the first one, we would do inverse cosine of -9 divided by, I need parentheses, 5 square root of 10. Probably would have been easier if I would have left it as square root of 250 at that point. We get 2.17-ish, 2.176 for that one. That one is in quadrant 2. Pi over 2 is about 1.57 because pi is about 3.14. 1.57 is half of that, right? So this is the angle we want. Okay. Here's where the be careful comes in. I should get the same thing if I use the inverse sine of 13 divided by 5 root 10. Oops, I forgot the parenthesis. I hate having to use the mouse every time. I didn't get the same answer, did I? Okay, but here's where the be careful part comes in. Remember this angle, I'm going to draw on the board for a second. This angle here is over here in quadrant 1, right? When we do inverse sine, it's in quadrant 1 or quadrant 4. Since it was positive that we did the inverse sine of, it ended up in quadrant 1. Instead, we want the one that's over here in quadrant 2 with a reference angle of 965. Right? How would I figure out what that angle is? What do we need to do? Subtract from pi. Fantastic, right? It's basically 180 minus that, but we're doing things in radians, so we want to subtract it from pi. So if I do that on here, do pi minus the answer, I should get the same answer as what we got for the inverse cosine. We better, right? Okay. This is why I said be careful. And another reason why I'm doing this right now is this is going to pop back up again here in a little bit. Next week or the week after. When we're solving equations, this will pop up. Okay, that's why I'm mentioning it now. Okay, make sure that the angle you're finding is in the correct quadrant. Okay. Again, if you do both of them, both your inverse cosine and your inverse sine, and find the correct angle, they should match. So this is another way you can check your answer. Okay. So the angle we want is about 2.176. So if I go back to the original problem, we get -9 sine of 7x plus 13 cosine of 7x is 5, I should say approximately, but I'm going to write it this way, 5 root 10. And you could, at this point, you can make a decimal for that too, if you wanted to. And then it'll be sine of, what goes on the inside now? 7x. And then plus what? Yeah, the 2.176 angle we just found. Yep. Yeah, this one's not going to be in terms of a pi, some multiple, fractional multiple of pi, because we're not finding the exact value. Questions on that one? Is okay? All right. So that finishes up section 2 in chapter 7. So next time we will get into some more formulas. We'll do what's referred to as the what are we doing? We're going to do we have double angle formulas, half angle formulas, and product of sum formulas. That sounds like fun, doesn't it? Sure. Just a reminder, a week from Friday, we have exam. Okay, so we'll talk a little bit more about that as it gets closer, but we do have an exam a week from Friday, just to keep it on your radar. All right. Have a good one, everybody. We'll see you on Friday. Hopefully it'll be cooler.